Okay, this is part 2 of our videos on proof by induction, and today we're looking at proof involving divisibility. Now, it's exactly the same as the first video in terms of the language used at each step of the inductive process. So we start off by looking at what they've given us, and what they've given us is they've given us that n belongs to the set of natural numbers, and we know that the set of natural numbers is 1, 2, 3, going on forever, and we know that the smallest value of n that we have to use is n equals 1. So therefore, when we come over here to step 1, which is show true for the smallest value of n, show true for n is equal to 1. So now, the thing is, on this particular inductive process, there's no left-hand side and right-hand side. There isn't. So what you've got to do is you've actually got to create a left-hand side and right-hand side. So what I do is I let f of n equal to 4 to the power of n minus 1. Now this is very important. You can't do this without adopting this approach. So I now want to see whether the statement is going to be true for when n is equal to 1. So now I write down f of 1, and using the empty bracket, it's 4 to the power of 1 minus 1, and of course 4 to the power of 1 is 4, 4 minus 1 is 3. So I have now done it for the smallest value of n, which is n equals 1, and I've got a value of 3. And the big question is, I had to prove by induction that 3 is a factor of this formula. Now, I'm looking at here, is 3 a factor of 3? And of course, the answer is yes. 3 is a factor of 3. 3 divides into 3. Therefore, shown true, because 3 divides or is a factor of into 3. Doesn't matter which bit of language you use, whether you use divisibility language or whether you use it's a factor of. It doesn't matter. So step 1 is done. So now we're going on to step 2. And we need to keep this as neat as we possibly can. So I'm going to put a little bit of a border there. We want to use as much space up or as little spaces as we can. So step 2, I'm now going to assume, step 2, I assume true for n is equal to k. That is the inductive statement for step 2. Now, what does that mean? I've got at the moment f of n is equal to 4 to the power of n minus 1. Therefore, I've now got, replacing the n with a k, f of k is equal to 4 to the power of k minus 1 is divisible by 3. Assumed. Doesn't matter quite what language you use, as long as you tick the box. So we're assuming that 3 will divide into 4 to the power of k minus 1. We're assuming that. Another way of saying that statement is that 3 is a factor of 4 to the power of k minus 1. So there's interchanging of language there. We're now going on to step 3, which I'm going to squeeze down the bottom here. So step 3, same as the previous video, is need to show true for n equals k plus 1 using step 2 and possibly step 1. But we have to use step 2 for the proof. So now what I need to actually say is, okay, we need to show true for n equals k plus 1, so we need to use a bit of language here. Therefore, need to prove that f of k plus 1, because we are going to replace the n with a k plus 1 now, and we replace this n here with a k plus 1. So we need to show that 4 to the power of k plus 1 minus 1 is also divisible by 3 using step 2. So we need to show that this is also divisible by 3 using step 2. Proof. Proof. F of k plus 1 is equal to 4 to the power of k plus 1 minus 1. At this stage, it could be that some of you watching this video will only get as far as the next line, but it's very important to move this problem on. And what you're looking at is you have to rewrite it eventually so it begins to look like step 2, so that you can use the mathematics from step 2 in order to be able to do it. And what step 2 has is 4 to the power of k. So in order to make this look like step 2, I need this looking like 4 to the power of k. So I'm going to use the addition law of indices. And so we're going to go back and I'm going to write 4 to the power of 1 on 4 to the power of k, because the addition law says that you're multiplying the bases with the individual powers. So I've now got that. So, how do you do the next line? Well, the problem is, it's a major problem here. That says one of them. And at the moment, I've got 4 of them. But I only want one of them. So I need to make it looking like step 2. So what I've done is I've changed that 4 to 1. Now, clearly those two lines aren't equal. So what have I got to add on to make the lines equal? Well, I've got 1 of them. I need 4 of them. So I have to add on how many? Pause the video. Think about it. And how many do I have to add on? I have to add on, I had 4, I've written down 1, so I've got to add on 3 more 4 to the power of k's. So I've got to add on 3 more 4s to the power of k. So 1 plus the 3 gives me 4 lots of 4 to the power of k. And this is the trick. So what do I now know about this line here? Well, this line here has now got step 2 in it. This is step 2. And what is step 2 equal to? Step 2 is equal to f of k. So you can put that in now. You can now replace this with f bracket k plus 3 lots of 4 to the power of k. Now, what do I know about this item here? Well, I know from step 2 that this is divisible by 3. So this is divisible by 3 from step 2. And what do I know about 3 times something? Well, anything multiplied by 3 definitely is divisible by 3. So I can also write here that this is divisible by 3. And of course, go back into the original question, it showed that 3 is a factor. Well, if 3 divides into something, then 3 must be a factor of it. So again, the language is interchangeable. So therefore, I finish this off, therefore f of k plus 1 is also divisible by 3 or 3 is a factor of it. So that is the end of that particular section of proof. And the final thing is step 4, proof follows by induction. Okay, before I move on, let's look at what the inductive process says. The inductive process says that step 1, I know my first domino topples. Up here somewhere, I've got what I call my kth domino, and I know that if I assume that my kth domino falls, I have just proved that if this falls, it will topple the next one. And if it topples the next one, what happens then? It will topple all the dominoes. So therefore, it will continue to topple everything. Hence, the proof follows by induction. But the reason why this works is because I've already shown that domino number 1 actually topples in step 1. And what I've proved here, that if a domino topples, what does it cause the other domino to do? It causes the next domino to topple. That's what I'm proving in step 2 and step 3. That if the one before topples, it will topple the one after it. And therefore, that's why you need step 1, and that's why the inductive process works. Okay, I thought I'd mention that now while it was still fresh in your minds from the previous video. Let's move on to the next example. And now there's a sense of déjà vu about this. You know, it's the same thing over and over again. So what we have now is n is equal to the set of numbers 1, 2, 3, dot, dot, dot. We know that the smallest value of n is equal to 1. So we know that the smallest value of n we're going to be using is n equals 1. You know already from the previous example, this hasn't got a left-hand side, so therefore we have to create a left-hand side and a right-hand side. So therefore we let function of n equal 10 to the power of n minus 7 to the power of n. And then we get started. So here we do step 1, and step 1, show true for n equals 1. And what we're looking at here is we're showing that it has a factor of 3. It's divisible by 3. So we do f of 1 is equal to 10 to the power of 1 minus 7 to the power of 1. 10 minus 7 is equal to 3, which is divisible by 3, which is divisible by 3, therefore shown true. So we have now shown that the first domino topples. We have shown that the first domino topples. So over here, trying to keep space used up at a premium. Step 2, assume true for n equal to k. Therefore, replace the n by k in the formula, and we've got f of k is equal to 10 to the power of k minus 7 to the power of k is assumed to be divisible by 3. It is assumed to be divisible by 3. Now we're on to step 3. And step 3 show, need to show, prove. Doesn't really matter what the language is, as long as you convey what you're trying to do. You're trying to show true for n equal to k plus 1 using step 2 brackets possibly 1 okay, so statement is easy to make, but now we've actually got to write it in mathematics. Therefore, showing that f of k plus 1 equal to 10 to the power of k plus 1 minus 7 to the power of k plus 1 is divisible by 3. And if you want to write in using step 2 again to reinforce what you have to do, then please by all means do so. Okay, so what do we do now? We do the proof. And what you've seen from the previous page is the trick. And the trick is we need to make, for divisibility proofs, we need to make this look like the previous step. And the previous step quite clearly states we've got a 10 to the k and a 7 to the k. So we're going to use the addition law of indices in reverse. So we're going to do 10 to the power of 1 on 10 to the power of k minus 7 to the power of 1 on 7 to the power of k. And you've got the first line of step 3 right, and if you really were under pressure and couldn't do what you're doing, you could stop there, pick up the method marks, go to step 4, write the statement down, and, bank a few marks for the exam. Now, the thing is, at this moment in time, I've actually got 10 lots of 10 to the k, and I should only have one lot. So what I'm going to do now is I'm going to write in here, I should only have one lot of 10 to the k, because that's what it says up here, one lot of 10 to the k. Whoops, I'm short 9, so I'm going to throw them in over here straight away. Does the step 2 have a minus sign? Yep. So I've definitely got the minus sign, that's handy. And what I have here is I've got one lot of 7 to the k. So I've only got one lot of 7 to the k. Now, the problem is, be very, very careful, you don't want to lose a silly mark. You've got minus 1 and you should have minus 7. So what have I got to do to minus 1 to get back to minus 7? Well, I've got to do minus 6 of them. So there you go. Now, we can do a bit of a tidy up line if you like, or you could just recognize quite simply that at this moment in time, this is the equivalent of step 2, and step 2 can now be replaced, 10 to the k minus 7 to the k can be replaced by f of k. So we've got f of k. Now, this is where you have to take care. You could factorize out the 3. Some people don't. What they do is they, without thinking, and let's pretend we're in the exam, we're under pressure, and you do it without thinking. You actually literally write down what's there. Is that the end of the world? No, it isn't. Because here you can say divisible by 3 using step 2, because we assumed f of k is divisible by 3. What do we know about 9 times something? Well, 9 times something is clearly divisible by 3, isn't it? And what do we know about 6 times something? Well, it's clearly divisible by 3. So what we can actually write for both of these now, each of these terms are clearly divisible by 3. So therefore, every single term is divisible by 3. Therefore, f of k plus 1 is proved to be divisible by 3. And I've finished step 3. And of course, the last bit now is squeeze it in. I'll see if I can squeeze it in down the bottom. Step 4, proof follows by induction. Now, quickly moving on, there is one more type that is on your course for divisibility. So we've seen a single power, we've seen a double power situation, and now we're just seeing a polynomial type where we've got to prove that this is divisible by 2. Once again, we know that the smallest value of n is going to be 1 because we are allowed to pick n from the set of natural numbers. We know from the previous one that we can let f of n, well, we have to, it's not, we have to let it equal to f of n is equal to n squared plus 3n. Step one actually says show true for the smallest value of n. So show true for n equals 1. So therefore f of 1 is equal to 1 to be squared plus 3 on 1. And 1 to be squared is 1. 3 on 1 is 3. 1 plus 3 is going to give us a value of 4. And 4 is clearly divisible by 2. Therefore, shown true for n equals 1, because this is clearly divisible by 2. Okay, we're now on to step 2. And step 2 is the assume step. Assume true for n equals k. Therefore, f of k, which is equal to k to be squared plus 3k, because all we do is replace the n by k, is assumed to be divisible by 2. So we're now on to step 3. And step 3 need to show true for n equals k plus 1 using step 2, possibly step 1. Now, once I've made that statement, I need to write down what I'm talking about. So at this moment in time, I've got f of n is equal to n squared plus 3n. So therefore, f of k plus 1 is equal to empty bracket method. Replace the empty bracket with the n with a k plus 1, plus empty bracket method, replace the n with k plus 1. So need to show true for n equals 1. Therefore, need to show this is divisible by 2. Okay, let's look at the proof. And the proof is, what do I do this time? Well, I can't think of any other thing to do except expand this out. So we're going to expand this out. Now at this stage, you can pause the video and do the expansion and then check to see if you've got it right at the end. So pause the video now, please. Otherwise, it's going to be k squared plus 2k plus 1 plus 3k plus 3. Now, it's very important you don't go all gung-ho on this, because when you've done the initial line of working out, then what you are doing in order to save work is you are going to go back and you're going to look at what you need. And what you need to make it look like step 2 is that k squared plus 3k needs to sit. It needs to sit on its own. So I'm looking down now. That's what I want. Do I have a k squared already? Yes, I do. Do I have a 3k? Yes, I do. So what I'm going to do now is I'm going to write those next to each other. K squared plus 3k. I might emphasize that I'm highlighting it. I'm looking at it by putting it just in a square bracket. And now what I'm going to do is tidy up the rest. So I've got a 2k. So here's my plus 2k. I've got a plus 1 and a plus 3. And a plus 1 and a plus 3 is a 4. What is that k squared plus 3k? Well, that is step 2. And what is step 2 notation? Step 2 notation is f of k. So I've now got f of k plus 2k plus 4. So, bit of English. What do I know about this? I know this is divisible by 2 from step 2. And what do I know about each of these? Well, if something is multiplied by 2, clearly it's divisible by 2. And if you've got the number 4 sitting on its own, that's clearly divisible by 2. So clearly, both of these are divisible by 2. And consequently, if each term is divisible by 2, then the whole thing must be divisible by 2. Therefore, f of k plus 1 is divisible by 2, because each term is divisible by 2. And finally, step 4, proof follows by induction. So let's once again quickly revisit what do we mean by the inductive process. Let's look at the analogy of the domino. What do we know about domino number 1? It topples. What do we know about any pair of dominoes? Well, what we know about any pair of dominoes is if k topples, we've now proved that k plus 1 automatically topples as a consequence of the one before. So what does the inductive process allow us to, what have we just proved? We've proved that that one topples, and we've proved that if this one does topple, it will topple this one, and therefore it will topple all of them afterwards, because there's a sort of what we call in English the domino effect. It leads on to this effect being repeated all the way through. But the reason why we prove this one is we now use the k toppling the k plus 1. That now means, well, 1 must topple 2, and 2 must topple 3, and 3 must topple 4, because we proved that if the one before topples, it will topple the one after it. And that's, again, the inductive process. Now, what I need you to do is to answer the questions 1, 9 and 13 from exercise 11.3 on page 275.